She actually joined microelectronics in 2006 and has had several roles in this company. First, she started as technology manager and later as advanced photonics pixel architect. And in this role, she led the advanced photonic sensor technology development, working in close collaboration with the silicon process module and system R&D teams to define and develop ST imaging photonics pixel roadmap and specifications, and actually developing the kind of SPAD sensors that most of us have on our mobile phones. So in her current role as the imaging communication manager, Sara defined her work is related to defining the communication strategy for the Imagine subgroup at ST Microelectronics, and she also coordinates all the academic collaboration of ST Microelectronics. She is the author of several patterns and author and presented papers on SPADs, so single photon avalanche diodes, and SPAD-based systems and application. So today she will be talking about sensors and what is yet to come related to sensors. And I welcome her here very deeply, and we are very lucky to have her here. So Sara, when you want, you can proceed. Thank you for being here.
Thank you, Paula, and good morning, everybody. Good afternoon, I would say. So today I will first speak a little bit about myself. Paula gave a little bit of an introduction, but I think, considering you're all quite young, I thought to give a bit of an overview of my career development. Then I'll speak about sensors. Specifically, I'll go into LiDAR sensors, which is where my expertise is, and then look a little bit at the architecture development. So I think this is quite interesting for you. And then the future, where you all come in, apart from maybe somebody that is a bit more on the retirement side, but we'll see that. So how did I get to become an electronics engineer? Well, I started off wanting to become a ballet dancer. So that was when I was a young child, that was my dream. But then when I was at high school, I saw my first circuit, right? It doesn't look exactly like the ones you see nowadays. It was an amplifier inside, one of these stereos, the disc players and so on. And I loved it. Right. So I thought, that's it. I want to do that. I want to draw. I want to design those things. I want to make them. So then I went to electronics engineering. So I went all the way to Milan, across the flat, about 50 kilometers away. And I did actually a degree in electronics, microelectronics and photonics was the focus of my degree. And here I saw my first MOS transistors manufacturing. And again, I decided that was going to be my focus for my career. I love the idea of making a device itself. And so then what I did is I took a bit of a longer journey, and I went all the way to Scotland to start a PhD in physics. And in fact, my PhD was about the design of an InGaAs, indium phosphide, single photon avalanche diode. And I was both in charge of the design and the characterization. So, I was in dark labs all the time, really, you couldn't have any light on because each photon counted. But I really enjoyed this. And at the same time, actually, to further my studies, I was also doing the coordination of a European project, which was also very useful to develop my kind of skills of networks and so on. And the people that I work now with are the people that I met then. So, when you do your PhDs and so on, going to conferences, going to places, it's important to establish these wider networks. And then I joined ST, back in 2006. I decided, okay, enough of research. It's too slow for me. I want something a bit higher, faster pace and so on. So I went to ST, and ST actually is one of the world's largest semiconductor companies. We have 50,000 employees, but it is quite a large amount of people working on R&D. It's more than 18%, and I'm in there in these numbers. We also have our own manufacturing sites, which is now a very unique advantage in terms of being able to devise your own, to design and to manufacture your own dedicated processes and devices. Again, going back to my dream, it's key. And as I said, we have really the manufacturing sites. So we have some manufacturing in France, Italy, Sweden, and also in the Far East, so Singapore. But we also have the kind of what we call back end, so where we do assembly and test. Again, quite spread across the world. And inside ST, actually, I started off as a characterization engineer. So that's one of the things I learned during my PhD. And I was looking at, characterizing CMOS image sensors. So at the time, we were working with Nokia, and they were the first image sensors in mobile phones when nobody believed they would ever take off. Who would use a phone to take images? Crazy. And then, after that, I had actually this broader skill set. Through my PhD, I also looked at process and so on. So I became what we call a pixel architect, which means I looked after the full development of a pixel from the initial concept all the way to the industrialization. So, defining really what process you need, what characterization steps you need, and everything that you need to modify to make it suitable for a device that goes into phones and so on. And now I am a communication and academic collaboration manager. So I decide basically the strategy of communication. So which conferences we go to, which events, and then also, I look at our collaboration portfolio and make sure that we are aligned with our vision for the future and our goals. So my job, I'm part of the technical staff in ST, and I'm a senior member. And I'm 90% full time because I am a mother first thing, so I want to spend time with my family, and so I actually do all of these in 90% time. And so what I do is, as I said, drive imaging subgroup strategy for the internal and external communications. I also follow, decide which academic collaborations we take through, little committees where we decide really which universities collaborate with and so on, which kind of European projects to enter and that. And then I also look after the STEM coordination. So there is a real crisis of engineers. We don't have enough electronics engineers. If you consider that pretty much everything that we use nowadays as a chip, or at least the transistors in it, right? The amount of electronics engineers we have is definitely too low. So I'm trying to tell children that actually, behind this black screen, there is something that they can work with, they can play with, they can design, they can make, right? Which is something that is very difficult when you're a child, that all you see is a black screen where you can program things and do whatever you want. It's quite a tough challenge, but I'm determined that we will make it. And then outside of ST, as I said, I do collaborations. I also am a technical reference for SPADS for all the research activities we do. And then finally, I participate to several technical committees in conferences. So, but I'm also a mother, right? My children are here with me today. They didn't come, but they are in Santiago. And so I had two daughters, 2 years apart. So this was when the second one was born. And I did take 2 times 6 months maternity leave. And the reason why I said this is because it's important. I see there are some females here, and actually, you don't have to choose between your career and your family. You can make it work. And then, I was lucky. I came back from maternity leave, and ST was starting to work on SPADS, right? My expertise of, the topic I was an expert in. And so really, I was at the right person in the right place at the right time. But, that's what you have to do. Every time you have an opportunity, grab it, right? Don't be scared. It's going to be, it's just there for you to take. So now let's go back to sensors, which is why I'm here, right? To talk to you about this. So how many sensors do you think are in a phone, in an iPhone? Let's take the iPhone 15. In fact, I think I took, so that one. How many sensors do you think are in it? I need a number. Come on, just try. 10? Somebody else? Somebody online who wants to dare? Well, you're not too far, actually. Actually, there's 9 types of sensors, right? So it's quite a large number if you think that the Nokia one had one, image sensor back then. So there's MEMS sensors, And they are for, there's a barometer for altitude estimation. There's a gyroscope for, to tell whether your screen is up or down. There's an accelerometer, again, for screen orientation, and then a magnetometer for the GPS location, and finally a moisture sensor. So nowadays, these have become quite popular. But we also have optical sensors, and actually there's quite a lot of these. There's a proximity sensor, which tells you, it's the one that switches off the screen when you answer your phone call. It's in all it's in all phones pretty much. We have an ambient light sensor that determines the screen brightness, and also it's used for deciding the white balance of your camera, right? A camera doesn't know what white is. It's your brain that makes white, irrespective of the illumination. So when you have a digital camera, actually that's a big challenge. So we use these ambient light sensors for that. Then there's the Touch ID. So that takes an imprint, like an image of your thumb. Then there's the Face ID. If you have an iPhone, you might be using it or not. And then you got cameras, right? And this is plural. And this is where I want to dig in a little bit more. So in fact, in the iPhone, there's front cameras. There are the ones that are here, right? And actually it's plural. So there's two. One is a ST's one, and one is Sony, right? And they use one for taking the images, the other one for the photo ID, the Face ID functionality. Then we have rear camera. So my phone is a bit old, so it's only two, but this one has actually four. There is a telephoto camera. There's a main rear camera. There's an ultra wide camera, and then there's a LiDAR camera. Unbelievable, right? It's inconceivable. I mean, considering that, as I said, nobody believed you would ever use these to take images. Now we got 4 cameras just for that. And actually, that makes a total of 14 sensors. So I think Vincent was quite close to that. Now, how many sensors do you think are there in a car? A bit bigger. So but it's a bit less clever. Then, any other? Come on, a number. 50. Yeah, that's a bit closer. Yeah, so there's more than 60, in fact. And this is a normal camera. Again, I took it from a website. This is the number. This is as many functions, and these are only the functions. So imagine, this will be replicated across your car, because also, cars need redundancy, so they need to have more of one thing, because if one fails, right, the camera still has to, the car still has to be safe. So this is a key element. And actually, and there's a lot of optical sensors now being added for autonomous driving or assisted driving even. When a lot of the cars now, when you reverse, there's a camera, it's super easy to now reverse park. I never had that before. And, what is coming again is LiDAR. It's another important aspect. And actually, we've been in this industry for a long time. Optical sensors is where we are. We started off in actually in 99 ST, when we acquired a spin-off from the University of Edinburgh. They actually had their first CMOS camera, which was for a toy, right? It's a Barbie cam. If you look back, like it was really a small camera, digital camera. And because it was a toy, there was no need for a high resolution, high quality image, right? So it was enough to have some kind of image for a toy to be deployed to start this technology. But then we sort of acquired this company, and we started working with Nokia, who believed that it was, like having a camera in your phone would be the future. Unfortunately, what they didn't believe in was a touch screen. And that is what was their downfall. And so, in fact, we worked with Nokia up to 2014, 2012, but then Nokia really collapsed. And, we had another project actually coming up again through the University of Edinburgh, which was a time-of-flight sensing. So, and this is where, we started having the provision in mobile phones. And this was through another collaboration, which was with LG. So in fact, we were wanting to use our time-of-flight sensor for displacing the proximity sensor, the one which switches the phone off. But in fact, actually, LG told us, well, it's much better for autofocus assist to tell you where to put the camera lens before you take an image when it's dark. You can think, when it's a dark environment, it's difficult to detect edges to define where the focus is. And that's where we started really selling these products into mobile phones. And then, okay, now we have different, in fact, optical sensors. We have global shutter sensors for automotive applications. We have also ambient light sensors and so on. So we have quite a large variety of devices, but I will be focusing really on the LiDAR, okay? Because that's where my expertise is. So who knows what LiDAR is? Do you know? Have you heard of it? Yes. So, well, it's basically a system that can measure the time light takes to reach a target and come back. Okay. And the way it does it uses the fact that we know the speed of light, right? It's well known. So once we have the distance, we can infer the distance from the time. And so all we need to do is really measuring the time it takes for this. And well, if we think about 1 meter, what we need to be able is to detect 6 nanoseconds of time difference between when the light was emitted to when it came back. Okay, so it's quite a challenge. It's very small numbers here in terms of electronics and in terms of signal rising edges and so on, signal durations. And actually, the error is even more important because it's if you think about you want only 1 millimeter or 1 meter, then we're talking about 7 picoseconds. So it's quite small, right? So main pixel characteristics for a LiDAR is sensitivity to light, right? So we want to be able to say, okay, well, light has arrived, so there's a signal, right? But also we want really the ability to measure the time. So we have really the ability to measure T1, T2, T3 every time there's light coming in. And so what we use is this pixel, which is called a SPAD, single photon avalanche diode, right? And so the SPAD is really the single element, right? This is a simple image of it. It's quite old. But basically what we use is a photodiode reversing, biased in reverse voltage. And the output is digital. So what it gives us is really this a very instantaneous response. So as soon as you get the light coming in, you have a digital output. And usually we can achieve about 150 picoseconds time resolution, which is not quite the 7 picoseconds that we would love, but close enough and good enough for us. And then okay, we can do both close distance and long distance. So that depends more on the optics you use. And then, so as I said, distance and signal intensity are these two elements that we need for the LiDAR camera. So I'm going to go into a little bit of electronics because I know I thought you're all pretty much electronics engineers, so a little bit of circuitry is quite interesting. So to actually use a SPAD, we need slightly more than just the SPAD itself. We need what we call a quenching. And here I'm going to present our passive quench circuit. So when we have no bias, right, if you recognize these as an IV characteristic, current voltage characteristic of your diode, when we have no bias, we are here. So the anode voltage is at 0. The SPAD output is up at this voltage level here, right? And then what we need to do is to bias the diode, as I said, in reverse. So we apply a high voltage, which takes actually, which is above the breakdown voltage of the diode. And actually what happens in SPADs is that when you are here, nothing happens, right? It's this kind of unstable equilibrium. And actually, but it is an equilibrium. So everything sits there. There's no power consumption. Nothing really happens. But as soon as you get a photon, what happens is you immediately go onto your IV characteristics. So there's an instantaneous current flowing. And actually you charge a parasitic capacitance that you don't see in the circuit. So you don't need to design this one. You don't need to add it, but it's there. And what it does, it allows the anode to go up very, very quickly, right? Just because your capacitance charging is very, very fast, fast kind of time. And when this happens, right? What happens is you're also going down your IV curve, and eventually you reach a point where there's no more current. Your voltage has gone up here, right? So your total voltage across the diode has gone down, and so you eventually reach a point of no current anymore. And so then you start what we call the recharge, right? So basically, slowly, your voltage, so the capacitance discharges on this this transistor, which is effectively biased where it is considered a resistor. So it is basically acting simply as a resistor. So you have this RC discharge here, which basically determines the output, the width of your output pulse. Okay. So this is the fundamental behavior of any SPAD that you see in literature. There's different approaches for quenching, but that's basically what you have. And then, okay, the circuit is a bit more complicated because we need a few more things. So we need, we have the high voltage, but then we also need, as I said, this quench transistor, which has a variable, tunable resistor. So when you change the value of your gate voltage here, you change actually the resistance of the transistor. So you can adapt a little bit that RC recharge curve. Then you have an enabling, so you can actually disable your SPAD. So if you want the SPAD to be not operational, because it might be a high defective SPAD, or you want to save some power and so on, then what you do is you actually enable this transistor, and the SPAD anode goes up to a voltage which makes it overall below the breakdown. Okay, so you can disable it. And you can also then you need an inverter actually to have a true digital output, because naturally it wouldn't be, it would just be an analog output. So that's really the final stage. And you can recognize here an inverter, just the two transistors here. And then, okay, we also enable it so we can mask the output if we want to. And so then if we look at actually the output, when we look at the intensity of the scene, the way the SPAD operates is not like a traditional pixel. So it doesn't matter what your current value is. It really depends, what matters is the number of counts. So the number of pulses that you get within a time period. So if you are in low intensity, you have very few pulses coming through. But what happens is, as you increase the intensity, you get a point where you have a lot of pulses coming through. Okay, so the intensity is given by the number of counts per time, over time. So it's count per second. And okay, so I had a little bit here, something about jobs, like actually we have analog designs and pixel design engineers that, to help us develop all of these, the SPAD and all the transistors and so on, because actually we need also to customize everything. So our SPAD pixel is customized. The transistors in our most recent technologies are all customized to perform these type of functions. So, there's quite a lot of work in there. Then, okay, so we have a quenching circuit. So we can have a look at two critical figure of merits, right? One is power. We know that we want to minimize power consumption, right? That's a key element. I mean, we need to operate inside here. Okay, so to operate inside here, it means that it has to be portable. It needs to have a very low power. And then we also want to maximize that count rate, right? What is your saturation point? Right, and that is really what we call here maximum count rate, because that really gives you when your pixel is saturated, beyond which you cannot do anything. I mean, there's no ranging you can do. And so, okay, we focus on the first one, and we just to remind you, we are talking about pulse amplitude and pulse width. So if we look at the power per pixel, what we want to do is really reduce this pulse amplitude, right? It's really so if we look at the power is really IV, right? So we need to reduce the current that is flowing through the anode. So we really need to either reduce Vx, so reduce this peak, or reduce the capacitance. Okay, but this is a parasitic capacitance, so you can imagine how complicated it is to reduce it. Right, so it's designing, so the layout of your pixel is a key part of the implementation of a pixel. It's actually quite important. And also, when we look at the transistors all around the pixel, right? Also the gate of the transistor are capacitances, right? So again, it's quite a big, you have to really take all these parameters into consideration. And so you cannot really work as a single person. You always have to work as a team. Everybody has to contribute to these kind of optimizations. And then if we look at the maximum count rate, actually we want to make that maximum. And so what we need to look at again is, okay, let's try to reduce this pulse width, right? Because the smaller the pulse width, then the more pulses you can distinguish. And so what we need to do, that's really dependent directly on this RC recharge. And so we want to make sure that these RC values are both minimal, right? And so what we need to do is reduce capacitance, which is consistent with what we had before. And then we had also to reduce the resistance. But there is a problem, and it's about the quenching capability, because if this becomes so small, then the current from the diode goes onto the resistor instead of going to the capacitor. And so you have something that doesn't work anymore, right? So again, it's always trade-offs. It's always a question of, okay, well, minimize it, but not too much. And so you always have to take into account a lot of parameters and a lot of different, there are a lot of things coming into consideration when you design a pixel like this. So then, and because of these, actually, what we need is actually to follow a flow. And we need to guarantee pixel performance throughout the lifetime of a pixel. So, whenever we have a pixel, okay, it doesn't just, it's not just okay on the first design, but it has to last, you don't want something to break as you're, during the lifetime of your phone, right? It has to last that long. And to do that, actually, I always compare pixel design, being a pixel architect, like being a chef. Right, and actually, I like the cake things. We all see now Bake Off and so on. I think maybe also in Spain it's taken on the Bake Off where people just challenge each other on cake. So first thing is the taste, the color, and the size actually, and that's what the customer tells me. Right, I want a pixel that has got this maximum count rate, this power consumption, and so on. So then what I do is, okay, I'll make it what you like, and so in fact the size and the size is actually something that is always important. We have to maximize the amount of light we get. So we have to do layout. As I said, capacitance considerations are very important. So layout, design of that circuit and everything that comes after it, and then also what you put in the pixel. So for that we use TCAD. We do use a lot of device simulations. And then you manufacture it, right? You bake it. And actually, for me, all the machines in the fab are like big ovens, right? You have to have the right recipe, otherwise your cake will taste horrible. And finally, you have to taste it. Does it do what you thought it did? Does it look exactly the same? And does it taste exactly the same or not? And so that continues actually. We have several flows of this. Usually it's three cycles from the first concept of a pixel to actually the full industrialization. So it's three repeats of the cycle. And so yes, we have a team of TCAD, pixel design, process implementation, and characterization. So that's quite important. And then okay, we have to put it. Actually, we have to take this diode and make it a LiDAR, because the diode itself doesn't really do anything. So just to remind you, okay, we need to have intensity and time. And this is what a system looks like. So actually I brought here for you to see is a little demo. And actually this is that guy there is on this board, which is not powered up. There is a simpler version of that one on this board. And this board actually has a display. And the display tells you the distance of the object in front of this one. So this is a 1-point LiDAR, effectively. And this tells you the distance you're at in centimeters. Okay, so you can have a little go. And then if you want to actually see that specific one, that's a 16 by 16 zones LiDAR. And it's on this board, and actually it's a small chip here. It's a bit more complicated from an optical perspective. So in terms of module construction, it's more. so on. But basically, so what this does is it's quite complicated because in fact, you need first thing, okay, you got your chip, which is here, right? That's your silicon that you design. But then you need to interface it to the world. So you need a substrate. And the substrate has to have specific thermal considerations because you want actually good thermal dissipation and not really have things heating up too much. And also you need to make sure really that the interface is good and robust for, be put in the phone. Then you need a laser. Okay, we spoke about being able to measure the light, but you need a source. So we need to put in what we call a vertical cavity surface emitting laser, which is in there. Actually, that's class 1. So even if you look at it, it's okay. You're safe, right? You're not going to go blind. And then, okay, we have the optical elements actually to make sure that you control the light that goes onto the scene. And then finally, you have everything that is reflected back. So some more reflective lenses and so on. And then finally, you have your SPAD array, which is your detecting. But when you are in a real life environment, you need it's not enough to actually measure the distance between the excitation pulse and the time here, because actually the excitation pulse moves differently with temperature than your SPAD sensitivity. So the two chips are separate. They have different temperatures and so on. So you cannot really just use the source. So you need a reference. And what we do is actually we use some internal reflections to actually create this reference of our starting point for your laser. And then we only measure the distance between the two detected laser pulses. Okay. And this allows you to compensate for temperature, for all ambient kind of situations. Okay, so we have a lot of challenges that we have to address. Actually, when we are in real life, what happens is, you've got your transmitter and receiver, right? And you have a target, which is, if we think about the world, it's the world on average is 17% reflectance, okay? And it's a 5-meter distance, right? So you emit about 1 quadrillion of photons, considering a 90-degree angle. And then you consider actually, oh, sorry, it went ahead without me. And then you consider a random surface. So that is called a Lambertian surface. So it means that each point of that surface will reflect, but with a fully Lambertian in all directions, basically, like really as a full dome, right? And so basically, you still have this tiny wee receiver, a very small receiver here. And so all you get is basically one signal event, right? Because even inside your pixel, you only have one pixel, you got one SPAD and so on. Then you have this SPAD sensitivity, which is not 100% and so on. So in fact, you send out a quadrillion, you get one signal. Okay, so it's a big challenge. And that is why actually, instead of having a 90-degree angle, what we do is we introduce all these, optical elements to reduce the angle, right? And the optical lens, actually, for this one, we use a special technology, which is called diffractive lenses, so that they remain very small. So if you look at our module, it's very, very thin, right? And we can do this thanks to some specific technology that we developed that allows us to have a very, very thin process just using CMOS. So you use nitride and you deposit some diffraction patterns on a piece of glass, and you have a lens effect. Okay, so we can do that, and it allows us to actually recover some of the signal because we can focus in, and so we have less, more signal going to one point and so on. And so we have mechanical and optical engineers that do this in case you were wondering. And also what we need to do is actually, instead of using a single SPAD, what we do is we put together, in this case, for 16. Okay, so that's the chip that you see there, uses one macro pixel, has 16 SPADs all grouped together. And that is really to compensate for this low signal situation. And actually, we still need to quench them. And we still need to put them together. So we consider them as a single pixel. So we need to go through an OR tree. So we kind of consider this as a single pixel. So all the SPADs go through one single, they generate a single output at the end. But basically, okay, so what we want to do is, we're not in darkness. We need to look at the world outside. So we need, you're using it in the room. So really the ideal situation is, to look at it in a night, beautiful night, it will be perfect. But actually the real situation is we work in bright daylight. And actually these devices have to work outdoors, right? We need to be able to have our phones working night, well, your photo ID has to work, your Face ID has to work when you're outside. So what it means is that, okay, instead of having something that looks like this, we have something that looks like that, right? And so how do you recognize your SPAD output in there? It's quite difficult. It's a big challenge. And you see also the kind of the photons arrive in all superimposed, and it's quite a large challenge. So first thing is, okay, let's have a look a little bit at the spectrum. Okay, so first thing is, okay, safety. So we cannot work at here where we would have the best performance for our devices. SPADs are silicon. Silicon actually has the best absorption here, right? But actually, unfortunately, we need a class 1 laser. You need to be able to look at it without being blinded. And so we need to go away from visible. And luckily, we found something here, which is a very low, it's where you have basically maximum absorption of solar light. It's at 940 nanometer. And silicon actually is able to absorb up to 1,100. So we're just in the silicon range, and we can work here. So what we did is, okay, let's put in some, let's use a VXL that emits here. Okay, so our laser has this illumination. And also let's put infrared filters here so that we reduce a little bit that background illumination that comes from the sun. But still, I mean, okay, we took away some of the illumination, but we still have a high throughput that we need to deal with. Okay, so because we still have a lot. And our SPAD, we have these all three. And our SPAD output are quite large, so each signal, each SPAD output signal is actually about 10 nanoseconds in the devices you're looking at. So it's 10 nanoseconds for the first one, so the one that does only the one point detection. It's a bit less for the other one, but the challenge is there. So what happens is, actually, if you have two SPADs going through an OR tree, you'll detect only one photon, one event. So it's a disaster. Again, it saturates immediately. So what you do is actually you put in what we call a pulse shaper. So just before your OR tree, you shrink down the SPAD output to 1 nanosecond. And that way, then, your OR tree output then becomes very clear. And so you're able to actually increase the dynamic range of your sensor, of your LiDAR, without necessarily having to work too much on the quenching. Because actually to take away a nanosecond from your quenching time, it's a big, it takes a lot of effort. So, but we can do it actually in a bit of a clever way using some electronics, and it works well. So yeah, so then we also have the pulse shaper. So ultimately what a pixel in that sensor looks like is like that. You have your SPAD, you have all your logic, right? And you also have some counters, because you need to count, the intensity uses basically counters for that, so digital. So it's all digital apart from the front end of the quenching. So otherwise it's all digital circuits. Then we have another challenge, which is the multi-object scene. So, when you look at something, it's not just one item that you have in your scene, it's more. So the one point detector that you have there is completely ignorant of how many things you have in the scene, right? It can only tell you whether there's something there or not and how far it is. So it doesn't really have any cleverness in it. But actually what we did is we developed for the other one, which I don't have a demo for here, we developed actually histogramming, where we can really represent each of the object in your scene as a histogram and tell you how far it is, and also how much intensity you get. So you can actually, for some materials you can infer probably the material it is of, because different materials have different reflections and so on. So it can be used actually for various applications, not just distance measurement. And then the only problem, the drawback is the intensity of power, and data, because data, when you have histogram, then you start having a lot of logic. And in fact, what we come out with is something that looks like that. The chip that is inside the non-power device that you have there looks like this. So you can see the SPAD array here, the return one, and we have the reference one. It's a small one here, which is also covered in metal. So we only let in a very small amount of light because the VXL inside that chamber, the intensity there is quite strong. So to avoid saturation, we really need only to let some light in through. And then all of this one is logic for the histogramming. So we have a microcontroller, some and yes, and that's it. And a VXL driver, you probably can see it on this side here, quite a large piece of silicon. And yes, so as I said, this can be worked. Okay, so it's a 4x4 or 8x8. So it does a bit of a map, broad map of the environment. And so that's the whole thing. But to make it, right, it takes quite a lot of effort. So I talked about this part here until now. But actually what, you first start with a pixel, then you start with all your analog and digital design and the architecture actually, because you need to think about, okay, how do you want to implement that functionality? There's various ways. And so we use a lot of simulation tools to actually inform us on what is the best approach. How many SPADs do you need? How many macro pixel? How many SPADs inside a macro pixel? There's a lot of considerations. Then we go into production here in our manufacturing sites. Then we need to develop actually the wafer level testing. So each device that we make has to be tested. And once it passes, so if it passes this first test at wafer level, then it goes into another manufacturing site part, which is about module assembly, because actually then you have to put the silicon in the module. And that actually requires a little bit more time. And then you have to retest it. So again, you have to check that actually nothing happened to your silicon when it was assembled, because, okay, there's a lot of, you can have actually something that goes wrong at silicon level. You could have something that breaks and so on, or you can have some little impurities that end up on top of your SPAD, so you can't see anything and so on. So there's a lot of things that can happen. So you have to retest everything before you ship it to your customers. Okay, so you can't just, be ignorant of that. But then, and at the end, you also need to have a full team that will help your customer to actually embed their devices into, your devices into their own. And so we have all this customer support, which we call application validation, so that we make sure that you never leave a customer stranded. And then, okay, there's also teams of program management, planning, and marketing. And actually, as electronics engineers, you could end up in any of these functions, any of them, because our marketing people, a lot of them are ex-engineers. So quite nice. Yes, and this is an example actually of that device that I don't have the demo for, but you can see here, the zones, and there's a distance there. So red is probably quite close, and then far away. And you can also do a little bit of gesture recognition. So it's quite nice. I wish I could have brought you the demo because it's quite powerful. But if you come to one of the conferences in the future, maybe I can show you. And again, here, as I said, we have electronics engineering doing all these, setting up these demos. They're very important for us. And then these devices, actually, as I said, we got loads of customers, mainly in China, actually, phone manufacturers for this autofocus assist. So, they're actually embedded at the back of the phone to help decide where to put the camera. And this is where we had the biggest volume, in fact, for this mass market approach. And the applications, actually, what we see is they can be anywhere. We have now, all these cleaning robots. that was one of our first products as well. And the challenges actually for these robots are quite big, because first thing they have to detect, first thing, you have a very shiny surface, so your reflection doesn't come back, right? It goes away. So that's one challenge to solve. You have floors that people, they can fall off, the steps and so on. So, there was quite a lot of work to enable this. And then, the other ones is, the one I like is the vending machines, right? They need to know how many things are left. So it's, like they use basically the time of flight sensors to tell you how far the product is, to know whether it's almost finished or not. So in all these, there's automated, even in some of the supermarkets now you have these, dispensers where you just pick out the thing and it brings forward. And so that's all done. We have a augmented reality, virtual realities, the goggles. So we're starting to try to introduce them into these ones and so on. So there's a lot of applications. Some of them we don't really know, because they can, we have suppliers. We only deal with suppliers to then give it to somebody else. Recently, actually, we were founding some drones. There you go. So, and where is the future? Okay, what's going to happen? So now what we see is actually we're able to go into new technologies. So we see that actually, we are much more free in a way to develop things. So, all those chips I've shown you, they were in a digital technology. So we were really forced to use existing processes to build SPADs, to build photonics devices. And it's quite complicated, because you have to rely, you have to take into account the fact that you're dealing with, you have to make your transistors still as good as they were. So you cannot do whatever you want with the process. But actually, when you go here, when you have a pixel wafer, then you can really go crazy. I mean, okay, within the CMOS constraints. But you saw, all these new cameras now, even from Sony and so on, you can really have a fully dedicated process for pixel. And it means that you have basically a wafer which is only for detection. And so you can have much more sensitive devices. You can really customize your technology for that. And this is what's happening now. And what we see, and the bottom tier actually remains pure logic. So, like we can go 28 nanometer, you can go for, like now there's the kind of crazy nodes. And what is even more interesting is these 3 layers integration, where you have the purely photosensitive wafer, right? Again, pure pixel. So even maybe you only have the in-pixel MOS, but then, you have basically an analog layer. But then you can maybe allow a little bit more higher voltages, you can still have a 2.5 reset voltage and so on, kind of a bit more flexibility on your gate, bigger, like the kind of higher voltages. And then really have the true advanced CMOS in a completely different layer. So this is really where we see things going. Sony has some products here. They use 2 digital. In fact, they use 2 digital nodes. One very advanced, one less advanced. But it's kind of to do all the camera, the image processing, and so on. So, but it's what we have in ST instead is what we call the sequential layer, where we have an analog layer. So it's a bit, it gives you the flexibility of this analog part, because actually, even if you look at the SPAD, I showed you the quenching, the first part of the quenching circuit is really analog. So it's about, sizing the transistor correctly, making it so that it does perform that that resistor tuning and the capacitor tuning. You really need to be able to adapt your transistors and be away from your digital constraints, because you can't really work with standard things for that. And so we started off with this, right? We're here with the iPhone with many sensors, and what's next? So where is it that you're coming in? And there's a lot of things that actually, as engineers, you'll be looking into, for the future. We see there's a sustainable design, and actually even a manufacturing level, is really looking at processing using less material and water. I mean, it's really a challenge to modify your process so it achieves the same quality, the same performance, by reducing the elements that you're using for it, reducing the power for it. There's also design solutions. How do you do power, lower power consumption? How can you make that quenching circuit more effective? And also silicon area. I mean, silicon has a cost. If you can produce exactly the same chip using half of the silicon area, I mean, that's going to be a fantastic achievement. And so again, and then there's artificial intelligence, and that is both for efficiency and security. I mean, we see that, we're talking about edge AI, and edge sensing, where you take everything to the sensor. So there is no more data transfer between the sensor and the host, because you lose security there, like all the privacy, when you transfer your photo to your device, instead of having just it kept, locally to your sensor, you're already risking, security and so on. And even data transmission, requires power. So if you can actually embed things in your sensor, and that's a big challenge. And I believe that, we can do a lot there. Then, okay, there's a sustainable product, new materials, reducing the test time. You saw it takes quite a long time to have your, all your sensor tested. That's cost and power. And then, improving also the measurement techniques. And there's a lot of work that goes continuously into optimizing your setups, because when you have millions of parts through it on a daily basis, we have now shipped 2 billion units of these devices in the last 10 years. So, it's a lot of devices to ship. And so if you can improve even a millisecond of your test time, it's a lot. And then, new applications. I mean, the world is your oyster, right? You can make, think about all the things that have happened recently in terms of, this robot cleaner. I would have never thought people would buy a thing that cleans your house when you're out. Actually, they're more popular than I could ever imagine. But they are coming. And also, we see the virtual reality. I mean, even in our fab now, we don't call technicians in anymore. We have our technicians, like when we have machines that maybe are not performing as we would like them to do, instead of having the experts coming in, they connect through virtual reality goggles to the people, the technicians that are in the fab, and make them trying to problem solve, so that you save, the time of people coming in. You kind of optimize your resources everywhere. So it's already very much used. Augmented reality, we see it coming, but it's a much bigger challenge, because it's about also including your world, your real world, into the virtual, right? So it's making these two worlds coming together, putting a vase, a fake vase, a digital vase on a table. It's a massive challenge. So again, I think it's so exciting. The idea that, there's so much still to do. We only set the basis now, there's still loads of stuff. And then we see also the improve, the kind of pervasion of health monitoring systems. Doctors are becoming busier and busier, so they want you to actually wear monitors so that to check, how you're doing. Like you can measure your own blood pressure now at home. You don't need anymore to go into the surgery. And you've got all these heart rate monitors. So it's amazing. And again, we see a lot there. A lot to do. Reducing power again comes into this. If you want something that you can really wear for a long period of time, you need it to be really almost self harvesting, self powered, and more. Here is only what I can see now, but the reality is actually, it's something that you can decide, and you have really you're in the right position to think about what could be the next thing. And that's it. So, okay, that's just another thing is, like, I think power, I spoke about it a lot, and we have a commitment actually to become carbon neutral by 2027. And it's a strong commitment. So there's a lot, especially when you have manufacturing site, but everybody contributes it. I mean, also, ST is also starting to measure how people commute to work, because each of us actually contributes to ST's total CO2 emission. And finally, okay, some thank you for, all the people that helped me to put this together. I took a lot of stuff from my colleagues and, all the people that I work with, Edinburgh, Grenoble, Kroll, ATC, Microelectronics, because you cannot make anything like this on your own. You really need to be part of a team, and ST is a fantastic large team full of experts. So it's important to acknowledge them. And also some funding from the European community, which actually, when we started this work, for this sensor that I showed you here, we didn't have customers. Or we had very little. So there wasn't really, when we started the project, right? Then throughout the project, we started really seeing things happening. But actually, if we hadn't had the fund, the important funding from the European community, probably we would have not continued with SPADS, because it was a lot of investment, then, and the European Commission actually helps, starting these projects, which might go nowhere, but in fact, they were a success. So that's me. Thank you very much. You have any questions? Oh, sorry.
Yeah, no. Any questions here? I'm just going to check if, because there is some people connected from. Is there any question from any of you guys connecting from Teams? Okay, if there is something, just write on the chat and we will check from time to time. So any questions here from the people here? So we had I think you had the opportunity, all of you, to see the demo, right? Yeah.
Do you have any questions on that, for example? Well, Victor. Yes.
So this pulse shifting technique you implement before, after the sensor, is it right in a way? I mean,
So the power consumption. So yes. So you reduce the power consumption, but there's a limitation because, as I said, the capacitance is something which is when you look at the pixel and you try to reduce the RC, as I said, you have a minimum R that you need for quenching, and then you have a C, which is your intrinsic capacitance. So you have something, you can go only so far. So for example, we had a more than a factor of 2 going from an older technology, which we call IMG 175, which was 130 nanometer technology, to when we went to the 40 nanometer technology. So that just because of the way, you could, the metal and also the transistor capacitance, or, the gate capacitance and so on, the dead time was reduced by a factor of 2. So we achieved less than 5 nanoseconds, in fact. So, but then you reach a point where you cannot, the technology doesn't allow you to go any further. So you have to introduce something else. So that was the pulse shaping element. That's more to do with area fill factor. So then it's the optics, right? So you want to optimize the amount of silicon that is actually absorbing versus the amount of silicon that you use for the logic. And so you have to, it's a trade-off. So, how much quenching do you need? And so because you need to add transistors to do the active recharge requires, more transistors. And at that point, you have a trade-off. You could make it an active quenching and have maybe a higher dynamic range because, it also saturates differently. But then we didn't really need to get there. And the loss in fill factor was deemed not worth it. Yes. Well, ceramic is very expensive. And also, you cannot really mold ceramic as you like. So from, you wouldn't really be able to build the optical, you see the complexity of the optical system. Also, I mean, I didn't bring the cutoff, there is actually, if I go back to the slides, we look at this. Okay, so if you look at it inside, it's quite a complicated system. So you need, this one, which is a separator. So you need to have no optical crosstalk here. You need, for example, in this case, you also have these features which eliminate the problem of having, so it's another crosstalk problem. So when you have a screen, right, because if you put it in the phone, it sits behind this screen, okay? So what happens is you have a lot of reflection coming straight into here before the emission reaches the real target. And so this is, for example, something that we could do in this plastic mold to avoid, the crosstalk from inside the phone case. And so, like you have a lot of things that, you can do easily with plastic, but in ceramic would be, to manufacture ceramic to that extent, I think it would be crazy. And also, and the cost.
And
Ceramic packaging is very expensive.
Possibly weight as well, right? Plastic is probably lighter.
Yeah, the weight, I don't know. I don't know from, to be honest, the weight, I don't know because, yes, I wouldn't be able, but yes, it's mainly cost, I would say, cost and flexibility. Yes. So for that one, so we use Zmax for the bigger system. We use usually Zmax because it's good enough for this type of problems. For the actual device itself, so when you look at the SPAR, we use Lumerical, which is a very specific simulation tool within the device. So it helps you to actually also define how the light enters into the pixel and how it propagates in the pixel. So we use two different tools. And now we're actually starting to use artificial intelligence as well in the optical simulations, because especially when we deal with these diffractive elements that I was talking about, to simulate those is very intensive in terms of time. It takes a week probably to do a full 1 millimeter by 1 millimeter square simulation. And so we're trying to use artificial intelligence for that, to optimize the simulation quality and time.
Yep. Yep. I think Danny has a question as well.
Yes. It basically does a first analysis of the histograms, so that you identify basically a centroid of your peak. When you have an histogram coming back out, like you accumulate, so you have a TDC basically that creates the histogram, and then you do a first image processing of the histogram, so that you identify where the peak of the various objects lie. And so then all you transmit outside of your sensor is the position of the objects. You don't anymore, unless you are in a specific mode, but you usually don't output the histogram at all. So it's all done on chip. Yes, yes.
There is a question on the chat actually from Miguel Heredia, who is connecting online, and he's asking, I'm actually going to read. Well, thank you for the great talk. I have the following question. You commented on the possibility of recognizing different materials from the histograms of photon arrivals. How could this be achieved, taking into account that the spot rising edge jitter can be as large as 150 picoseconds? Or did you mean just object recognition? So it's basically asking whether it's object recognition or actually recognizing these materials. Yes, I think this is the question.
Yes, thank you. So in fact, yes, it's not about looking at the photoluminescence of the material. In this case, would be really just object recognition. And we know that some materials have different reflection, reflection quality. So depending on the and then you can extrapolate. Obviously, you have to know pretty much what type of materials you might be interfacing to, because yes, otherwise the problem is infinite. But normally, I mean, if you are in a fairly known environment, then you should be able to distinguish just based on intensity of reflection, because you're also dealing with one single wavelength. You're a 940 nanometer. So it's an important aspect of it. You're not illuminating with a broad spectrum. And so you can, the materials will have a different reflection coefficient.
Yeah, coefficient, yeah. Okay.
Did I answer your question?
Miguel, maybe you can connect the microphone, or if not, write on the chat.
Can you hear me?
Yes, we can.
Oh, wonderful. I didn't know that I was audible. That's why I wrote. Yes, it fully answers my question. Thank you very much.
Welcome. Another question. No, in fact, you don't. I mean, in fact, you're not able. So when you detect the photon, you have no idea where it comes from, right? So it can be illumination, right, from the background. It can be your active illumination, or it can even be dark. Okay, so it's noise. The sensor actually has dark noise. In fact, like I simplified the slides because, of the audience, but, you have what we call dark count rate, which is really just in intrinsic noise in the sensor. And so what you do actually, you integrate for longer. So, you basically integrate for a period of time. And what happens is when you have the histograms, like that, normally what happens is you will have also the background here. But if you accumulate for long enough, then you start distinguishing your peaks. So there is, you have a signal to background noise that tells you, okay, well, if the signal to background noise is above a certain level, then you're sure it's an object. So it is actually related to the pulse you sent. Yes. Yes. So the jitter of the spot. So when we talk about spot jitter, so the uncertainty between the arrival of a photon and that digital output, in the spot output. So that's 150 picosecond. So you have that which is intrinsic. But what you do is actually you compensate by accumulation again. So when you create these histograms, actually what you do is you reduce that noise a lot. And so you go back down to several picoseconds, in fact, of accuracy. And then we have, in fact, what we have is a lot of specific algorithms that are actually clever in recognizing where the object sits. It's not just a centroid algorithm, it's quite a complex, but it's all, it goes beyond my knowledge.
So you click on exposure time.
Yes, exactly. Exactly. Thank you.
Yeah, Payman.
So yeah, so what we call a macro pixel is when so each one of these I would call a pixel. Okay, so it's a one single spad, and each spad has its own quenching. So if you see here, right, each spad has its own wire going out to the quenching transistor. So we got 4 of them all connected. So each of them is considered a pixel. Then because you are combining 16 of them all together, into this ortree, then we call it a macro pixel. So it's really just a definition that it's quite well spread, and it is because effectively you're combining the input from various pixels. So, but it's its function, it's exactly as if you had a giant spad, one single giant spad. Okay, but what it does, it gives you this opportunity to introduce the what we call is this OR tree, this pulse shaper. Sorry, what it does, it gives you the opportunity to introduce this piece of logic, and so it increases your dynamic range. Because each spad, I mean, we could use just the individual spad, but we would be limited at this 10 nanosecond. So the maximum count rate is 1/10 nanoseconds. So it would be, I don't know, I'm not good at that. 1 mega. Well, no, what is it? 10 megacounts per second.
I don't know. Yeah,
100. So what you do is actually, you improve it by an order of magnitude, and you get, by using this approach, which is much better than, if you had a giant spad, it would be much worse because, would be a large capacitance, imagine, so again, actually, if you increase the pixel size to have that sensitivity, because that's the other thing is, the fill factor of these is much higher than the fill factor of each individual spad plus its quenching, because you can optimize the way you lay out the quenching. For example, all your transistors, they can be really put together quite nicely. So, there's a lot of work of optimization of the layout. And so if you put all the logic block together, then you can place things so that you optimize your fill factor. So the fill factor is the amount of actual light sensitive silicon versus the overall area consumed by your circuit.
And you have a
Well, you mean a macro filter, like a macro lens? So the micro lens is here, but I don't have a specific. So the way we do it is actually we place it on each spad. You see that one is for this spad. So these are exactly those spads, those each of them has got metal. So you have the active area here, the metal here in between spads. So you're basically, each of them is it's on its active. And then you have the micro lens here. So it's only on top of the spads, and then you have nothing on top of the digital. So we don't have any, if you want, any lens actually which concentrates the light that lands on the digital side, right? We don't have that. I mean, we did some work with Leti, in fact, where they designed some Fresnel type lenses, these using these circular nitrides, to actually concentrate the light from the digital, that was landing on top of the digital into the spad. But it's not something, like industrially, I mean, this was what we had and it worked, it gave us enough sensitivity. So it's always trade-offs, okay, it would have been great to have the Leti 100% fill factor, but actually this was enough for our system. Yeah, so there's a lot of them that have started using indirect time of flight for this face recognition. We do have products that do indirect time of flight. So I think they are 1 megapixel resolution. So we do have they have that. So in fact, it's something that we started more recently. So it's what we call. Yeah, so here, in fact, yes, I think it was last year or the year before, right, they've introduced the indirect time of flight sensors. They work on a very different pixel technology, because instead of using SPADs, they use these phase sensitive pixels. Yeah, so where you have basically the ability to switch the two gates. So you have two gates and you switch them on and off so that you can detect the phase of your incoming signal. And they are very fast transition, so yes, so creating these pixels is quite a challenge. But yes, we do have those type of products.
Yes, actually Payman is working on.
Oh, is that what you're working on? Excellent, yes.
Okay, are there any more questions? Yeah, it was already, well, we sometimes have to complain to our doctoral students, "Oh, you don't ask enough things," but I'm very happy that this was not the case today. I would just like to make some final remarks, something I liked your presentation very much, but something I particularly like is something you said towards the end. You mentioned that all this work with these paths and so on, this began with this EU project. But that there was no like a specific funding from, I mean, no idea of a final product at that stage. It was basically research as far as I take. I think this is really interesting because ST is a company, and even if it got this funding from the European Union, of course, this kind of funding doesn't cover everything. So there is the cost of the personnel,
obviously.
fabrication, and so on. So, I mean, the fact that companies, and we sometimes think companies don't do research or don't do enough research, but it's extremely good that we have in Europe these companies that invest in research, and it's very nice to see these very successful examples of going from research to the actual a very successful industrial product. So this is really very
in
good.
fact, I mean, and it's very true for this part because here when I talk about these projects, in 2014, when we started this was because the University of Edinburgh, we actually engaged in a collaboration with the University of Edinburgh, EPFL, and Fondazione Bruno Kessler, designing a SPAD in CMOS technology. For at the time, it was for I think the application was health, something to do with health, and we had SPADs for what are they called? These MRI scans. Right, and they had that as a project, and they started working on the design of these sensors, for particle detection. And the first ones had a fill factor, the first SPAD circuit. So the SPAD with its quenching and a little bit of logic was basically 3%. I don't have it here, but actually we do have some slides on all the history of the funding. So we started off really with this collaboration. And that was the first SPAD we designed. And it's this SPAD that I have there, the little round thing that is quite ugly looking. Now, where is it in my slides? Here, this guy here was what came out of that collaboration. Then we had another collaboration and we went a bit further. So when we did so the first one was called Megaframe. Then we had this specific MRI application, which was which made us design a pixel where we had something more compact, like the one we have in our product now, right? Which had more SPADs together, and then what we call the macro pixel, because actually they are all sharing the same manual underneath. So again, was another concept that came through a collaboration. And so those early stages allowed us then to have something, when the market was ready, we had a product. But at the beginning, actually, we didn't, as I said, we didn't know what to do with it. We had something that we knew could be promising, but there was no market. And so we created the market, and it's a success now.
That's excellent. So yeah, thank you very much, really, for the presentation, Sara. And I think for all of you connecting remotely, we will close the session now, but we will like to thank you once more. So thank you for the very nice presentation.
Thank you very much.